right, let's scroll back down, but I'm going to start just giving you the context here, okay? So, we spoke of valence electrons yesterday, and I gave you a really simplistic definition. It was the electrons on the outer shell, right? So we can recognize that quite easily when we had an electron configuration or when we had an orbital diagram, which, how do we feel on that after practicing? Okay, good. Okay, so I hear different responses, but we are going to practice with valence electrons a little bit more because generally there's a lot you can find out from the atom. Valence electrons is one, and then also a lot about its reactivity. So one of the most important facts is, now that you know electrons control chemical reactivity, we have to talk about why that's the case and what elements are more reactive than others. So it's all based on electrons wanting to achieve stability, electrons wanting to achieve octet. That's what it's called, octet. What does octet mean? It means a full, like, it could mean a full sub-level, maybe not the full energy level, but just give me the simplest thing you think of when you hear octet. 8, right? So that's the full subshell has 8 electrons, okay? So basically, that's down here. So if an atom does have 8 valence electrons, it is happy, it is calm and collected, non-reactive. Which elements in the periodic table have 8 valence electrons? The noble gases. Some of you guys are with me, some of you guys are still reading. Just hold off for 1 second, okay? So I mentioned yesterday, and then it was the first thing written up here today, valence electron number is equal to the group number. So if you're looking at the periodic table with me now, group 1, group 2, skip, group 3, 4, 5, 6, 7, 8. All of these are considered noble gases because they're inert, meaning they're non-reactive, because they are perfect, because they have what? 8 valence electrons. So how many valence electrons does fluorine have? 7. It is so close to 8, right? Just needs one more electron, right? It is ready to steal, heal, and do whatever to get that electron. It will steal it from somebody. So am I saying it's reactive or non-reactive? Very reactive, right? So all the halogens only have 1 to get, so they will react super, super readily because they want to gain that extra electron. What about group 1? How many electrons do they have? 1. Okay? It seems like that's really far away from 8, right? But what's happening is, I'm going to point to potassium. Okay, there's potassium. If potassium loses that 1 electron, it backs up. So I'm going to back way up here to argon, right? It backs up because it ends up having 3s2, 3p6. What's 2 plus 6? 8. So it ends up having its last octet that it previously had before it gained that 1 extra in the 4s1. So all of group 1 just wants to lose 1 electron, and then they back up to their previous octet. So are they reactive or unreactive? Very reactive, right? What about carbon's group? Carbon. 4. Meh. Gain 4. Lose 4. It's kind of hard to tell if that's reactive because you're like, well, gosh, it's going to have to gain 1, 2, 3, 4, or lose 1, 2, 3, 4. That's kind of hard for an atom. They don't always like to lose or gain 4. That's just a whole lot to handle. So those are generally mediocre in their reactivity. They don't have a strong reaction. But like group 2, they have 2 valence electrons, right? So how would you claim their reactivity? So if we say group 1 is very reactive, I may not say group 2 is very, I would just say it's just reactive. It's reactive, it's not super reactive because it actually has to lose 2, not just 1. So we're basing it all on how close is the atom to octet. So all atoms are going to become ions if they are gaining or losing electrons. So that word ion is relevant now. So they're gaining and losing electrons in order to achieve octet, which in our electron configuration language, that just means whatever number S2, whatever number P6. Now, the little tiny atoms like hydrogen, helium, and lithium, they're so tiny they really don't even have enough room for octet. So I like to call their rule duet, because how many electrons are they ending up with? 2, 1s2, just because they're super tiny, okay? So you have the ability now, because now you know too much, okay? You have the ability to predict, hey, am I going to be losing or gaining electrons? And what is the charge I achieve when I do that? So this information here is the beauty of now understanding what valence electrons are and what they can do. So I'm going to go down to a periodic table. I will pull out my colorful one so you can write down some of this on the periodic table. Knowing that we want to achieve octet, your job is to now predict, am I going to gain or lose electrons? And gaining and losing is going to give me what charge. Okay, so in my group, I'm in group 1. How many valence electrons do I have? 1 valence electron. So 1 VE is how I write that. So I am 7 away from, I have to gain 7 to get to octet. Or, like I said earlier, I could do what? Lose 1 and I back up to my previous octet. What's easier? Losing 1, what's my charge when I lose 1 electron? +1, right? Remember, a negative charge, when you lose them, you get more positive. So your charge is a +1 charge. Same logic. Group 2, how many valence electrons? 2 valence electrons. Am I going to gain 6 or lose 2? Lose 2. It's easier to lose 2 than gain 6. What's my charge? +2. So when they form ions, these are forming +1s and +2 charges. Only when they form ions. Skip all the B group elements, which are the transition metals. They have variable, as you see, they have variable electrons. They can lose their valence, but they can also lose more. They're just a little weird, okay? Group 3, how many valence? 3. Okay, I have 3 valence electrons. Am I going to gain 5 or lose 3? What's my charge? +3. Group 4? 4 valence electrons. Gain or lose? Either, right? So I'm going to put plus or minus 4. There is a split, like in the group someplace, like the first half, they're small, so they gain electrons, and then the lower half loses electrons, but we don't have to differentiate. You're good. All right, nitrogen's group. 5 valence electrons, okay? Okay, so I hear minus, go ahead. Minus. Why minus 3? So it's closer to the noble gases. So we're in group 5. We can either go boom, 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 gain 3 electrons to look like the electron configuration of octet, or I can lose all 5. It's way closer to gain 3. So now we're hitting negatives. -3 as the charge. Okay. Group 6, 6 valence electrons charge. -2 or 2 minus, however you want to say it, because it's going to go boom, boom. Gaining 2 electrons makes it look like that of a noble gas. And then group 7, 7 valence electrons charge, -1, because it only needs to gain 1 electron to look like that electron configuration of a noble gas. So basically, everybody's trying to be good like the cool kids, the noble gases, because why? They're the most stable because they have 8 valence electrons. So whenever you gain or lose electrons, have I changed my identity? Have I changed who I am? If I'm nitrogen and I'm gaining 3 electrons, have I changed who I am?
Yes.
No, I'm still nitrogen. Did I change my protons?
No.
Protons determine your identity, right? Protons determine your atomic number, which is who you are. What did I do? I'm saying, oh, I look like neon, or I look like neon because I've gained 3 electrons, but it's not really who I am. It's just my electron configuration looks like that of neon, which makes me a more stable compound or stable atom. Got it? So I'm not changing protons, not changing the identity. I'm changing the way the electron configuration looks so that it's more stable. Got it? Okay. So that's really the big idea for today. I just want to tell you 2 more things regarding electron configurations. You did a great job yesterday. Okay. We're going to practice ions just one more time because that was only question 7 on the problem set. I want you guys to write the electron configuration for magnesium. 2 for magnesium first, and then do magnesium 2+. Okay, so magnesium first. And I'm good to chant with you if you're ready. Magnesium. 1, 1s2. Keep looking up periodic table. 2p6. And that's where we end, right? Okay, so this is for straight up magnesium, the atom of magnesium. Looking at this atom, you can tell 2 ways. 1, look at magnesium on the periodic table, right? How many valence electrons does it have? 2. How many valence electrons does it have up here? You're saying that questionably. We know it's 2, but where are they? Where are they? 3rd energy level. So we can think about it cheating and look at the periodic table like, oh, it's in group 2, it's 2 valence electrons. But if you're looking at the electron configuration, don't forget it's the outside shell. The very outside is the 3rd energy level. Hence, those are the 2 valence electrons. Hot dog, what happened? Magnesium. What happened to it?
It
Lost the two, I'm going to put VE for valence electrons, from where? The third energy level, because one, it's the very outside. It's super easy to just swipe those away from magnesium, and we've already knew the prediction. If you have two valence electrons, you're losing two, you form a 2+ charge. Now this makes sense why I was telling you this charge is up front, because you didn't know how to predict, but now you know how to predict, so you should be able to predict the charge of any of those groups 1 through 8. So this one's electron configuration is going to be 1s2, 2s2, 2p6, because we're swiping these, right? So who does this electron configuration look like? Who does it look like? Say again? So magnesium, back that baby up, 1, 2, neon. Neon. So the electron configuration looks like neon because 8 valence electrons, because it meant it's octet. But is it neon? No, because we never changed the protons. Okay, good. So like if I gave you 1s2, 2s2, 2p6, and I said, who is this? Could you figure it out? Yeah. You could give me some options, right? Yeah. But there wouldn't be a true answer, because like the best answer would be neon, because it's showing 8 electrons, and naturally neon has 8 electrons. But it could literally be anything. It could be magnesium 2+, it could be sodium 1+, it could be fluorine 1-, it could be oxygen 2-, it could be nitrogen 3-, it could be so many things, because they all converge at neon when they form a stable ion. So that's why I would never give you that, like, who is this? Unless I gave you a hint and said it's neutral. Can I move on? Yeah. Yes or no? Yes. Yes, okay. All right, so those like uranium and lead ones, those were just the worst. Why? Okay, because it took more paper. What? Okay, so there has to be a shortcut. Here it is. Ready? So now that we respect the noble gases, we know how special they are. Now that you know that, I will tell you the shortcut. Okay, it didn't kill you to draw the long handout, but this is the shortcut. What you do is you bracket a noble gas. Not just any noble gas, the last noble gas you passed. So look back at magnesium, right? Magnesium, who's the last noble gas it passed? Neon, right? So for the example we just did, magnesium, it's not that long, 1s2, 2s2, 2p6, 3s2, but just for clarity's sake, the last noble gas it passed was neon. So you bracket neon, and that to me means 1s2, 2s2, 2p6. That's what that means. Then you go to neon, you go, okay, get me now to magnesium. What do I have to write? 3s2. Boom, done. I unfortunately and fortunately am not kidding you, because that would be, that would be a bad joke. So, who is this? Who is this? Point at argon, and then move forward as it states. This is zinc. Okay, who is this? Calcium. Okay, so these are called shorthand electron configurations. Okay, I want you to write the shorthand electron configuration for lead. Lead. Shorthand electron configuration for lead. That one's going to take you just a minute to figure out who's the last noble gas, though. You should be able to check yourself on the board now for lead. So this is way shorter than we did the first, like yesterday. Okay, so you're welcome. You had to build up some stamina first, because if not, you wouldn't know how to do longhand if you didn't have a whole day to think about longhand. Shorthand, you're like, got this. You know how to write longhand? You know how to write longhand, you can do shorthand. Lead's last noble gas was xenon. As you proceed forward from xenon, you hit 6s2. Stop, think, insert F block. First row of F block is 4F14. Go back to D block, follow through D block, 5D10, and then finish that last tail end, which was 6s2 and 6p2. How many electrons should this still represent? 82 electrons, because even though this is here, this is representing how many electrons? I'm hoping it's 54, right? Okay, so that's 54 electrons. It's just in brackets. Good? Okay. Can I go past this? Okay. I was going to have you try some more. Do you feel comfortable with noble gas for pet?
Yes.
Okay, you have some practice on your, you can practice more on your concept, but I'll come back to this. So, there's one more thing I have to tell you. Is excited state, did you see, I think it's question 6, mentioned something about excited state. Okay, so that's what this right here is, okay? Actually, I think it's the exact question, so just make sure you write problem set 5, like this was a problem. So we did a lab already where we excited electrons. What lab was that? We've only done one lab this year. Okay, we've done 2 labs this year. Benium and the spectroscope lab. Okay, what do we do in the spectroscope lab to excite electrons? So I electrocuted them, right? I was the electrocutor on that little box, and I was like, look at the light. But then you guys did what at your stations? You turned on the lamp. Literally, you electrocuted them to just lower voltage. So you've electrocuted some electrons, and there's like a gas in that bulb. And that gas is by itself, colorless. You don't see any light coming out of it until you light it up. And you're throwing electricity at it, so what are you doing to the electrons? You're going from ground state, hitting it with some electricity, you go up to excited state, and then it can't stay there very long. What does it do? So it goes from excited state to, and as it goes to ground, it releases energy. So what you are seeing is the release of energy. You don't see it get excited, you see it fall from excited to ground. So we've done that, and so remember, there are other ways to excite these electrons. So what are we doing today? We're exciting it with fire or heat, okay? So we're going to do that, but let's talk about the electron configuration for that first, okay? So as you take this electron and you bounce it out to a higher energy level, you're sending it to a new n number, right? So if it was n equals 1, you might send it to n equals 2, or you might send it to n equals 5. There's really no logic to which energy level you send it to. So let's go ahead and write calcium's full electron configuration. 1s2, 2s2, 3s2, 3p6. Alright, and we stop, right? That is the electron configuration for just a singular neutral atom of calcium. Alright? So if I excite an electron, many times it's not going to be the inside electrons because they're kind of shielded. It's going to be the last electron here, the valence shell. So what's the valence shell here? 4, right? So this is the valence shell. So what I'm going to do to write the excited electron configuration is you're going to write same thing, 1s2, 2s2, 2p6, 3s2, 3p6, and then instead of leaving that ground state, because this is currently a ground state electron configuration because it's not excited. So we're going to take this and throw it into an upper energy level. What do you want to do? 5 makes sense, right? Just go to the next one. So either you can write 4s1, leaving 1 electron where it is, and put 1 in a higher energy level, like that, or you could have done all that and then just said, nope, I'm going to scooch both of them up. I'm going to excite both of them and put 3p6 and then 5s2. As long as you're putting it out of order. Like normally we'd have to fill all the way to 4s, and then go sequentially from there. But I've gone out of order because now I'm putting it in 5. Basically, that means that's a solid state electron configuration. Thumbs up when you're good with that. All right, so I could have thrown it into 6 or 7, or I could have put it into 4. But for what? Because if the ground state is 4s, I could have gone to a slightly higher energy sub-level, so I could have thrown it into 4p or 4d, as long as it's higher than 4s. So there's many, many options here. Alrighty? Okay. Read for a second. And I'm doing this because you guys are very meticulous at making tables. It takes you a good half hour to make a data table sometimes. So I printed a nice data table. Some of you guys are like, no, we're not going to do that. We're going to roll the data table the whole time. Make sure I passed in the back. So what we're going to do, your purpose, go ahead and write purpose at the top. Okay. Now, I'm not going to even, one more, pass this. Do you guys need any more? Okay. So I'm not even going to have you really pull out the lab notebook because I'm going to tell you the instructions and I'm going to demonstrate it up front and then you're going to do the lab. Okay? So you can imagine, based on what we just talked about with purposes, we're using fire to excite electrons. Do we see that excitement? No, we see the result of the excitement. We see the release. Okay? So you're going to watch and learn first. Before we get started, you have to prep your Bunsen burners. If you don't remember how to prep a Bunsen burner, you will pull up the lab notebook because I'm not the only source of knowledge in this room, okay? Follow the instructions as I tell you. Switch solutions. So I only have 5 or 6 solutions per lab station. If you don't have a solution that's on this paper, there should be one nearby. And if it's not nearby, just ask nicely, like, group 5, you guys have lithium chloride, LiCl, and then they'll give it to you. And as we get back there, I will tell you about the loops and how to use those. I do have to clean them every year, so please don't contaminate them. Keep them with the solution they are paired with. So what you're going to do first is you're going to go through all these knowns. And these knowns have a specific color associated with their flame, and so you'll write the color of the flame. Then you can take a series of unknowns, unknown number 12, unknown number 5, unknown number 3, and you just write the unknown number here. And then you write the color of their flame. You must identify the species, the compound it is, based on your previous knowledge. Does that make sense? Okay, and then you have some questions. Alrighty? So, if you would, you have about a minute to get to some lab stations. Divvy yourselves. Set up your lab, your Bunsen burner first, please. You can kind of be in the same ones you chose last time, but spectroscope lab areas is fine. If I have to divvy you, it'll take me a Alright, guys, I'm going to cut you some around 9 big plates. 8, 7, 6, put the striker down. 5, 4, if your lab group doesn't have goggles and you guys are doing it wrong, then I have too many lab stations. Way too many. If you guys can't count, then I will count for you. I got 4 people up here and I think I got 7 or 8 back there. They can happen. I'm not begging you to figure that out. There's nobody in here? Nobody? Oh, come on, guys. Alright, so Bunsen burners is set up. If you're not sure, then go ahead and look in the lab notebook. I'm waiting on you. There should be no question marks at the lab notebook. Please do not strike yet. I just said set up. I didn't say light. Set up. Okay, this is ready. Alright, and eyes over here. Eyes over here in 5, 4, 3, 2, 1. Alright, so you guys just make sure you're ready. Go ahead and try your Bunsen burner and make sure it lights. We're going to wait on these Alright, Mia, turn it off. Off. Start over. Start over. It's not correct. 3 strikes and you're out. Start over. I'm not big enough. Well, it's so Gosh, guys, we're not getting to laugh today. Turn it off. Turn that off. It's not right. Got it. Alright, you need to turn your flame down. Alright, and 3 strikes and you're out. Off. The gas is off, guys. The gas is Alright, and 3, 2, 1, strikers down. Stop touching the Bunsen burner. Stop touching the Bunsen burner. Alright, so I trust that you can read back to your Bunsen burner line and get this right. I'm not holding your hand on this. So if you do not remember, you still need an inner loop cone. That means the oxygen, which is the barrel. There's a gap in the little threading. That's where the oxygen's coming in. So that's how you're going to get an inner loop cone. So if you're not there yet, you will be there just in a second, okay? So I have a couple groups, their flames are waving. It's just because we need a source on gas, where is the gas, or which area here controls the amount of gas. The bottom, which that's the gas valve. So a couple of you guys are saying, the thing on the bottom or the butt, right? That's how I got you to understand that first. But the gas comes in through the bottom, the oxygen up top allows for it to get enough oxygen to combust. So at this point, I'm going to demonstrate just how you're going to approach this, and then when you're ready, you can go back to Bunsen burner 101. Okay, so you have a little container, and so for example, this one says CuCl2. So on your paper, it'll say CuCl2, or it says copper fluoride. The magic stick, the loop on the very end is what you're going to get the solution in. So all you do is you open up your solution. Someone can request you just because it's cargo. And you just dip your loop in, you get a little bit of solution in your loop. You can actually see this one because it's blue in color. And one of your maybe other members will close up that for you just so you don't want to spill it. And at this point, I'm going to stick the loop inside the side of the inner lubricant, not in the lubricant, but the side of it. So if you can't see this, okay. Now that burns off in like no time. It burns off in 3 seconds. You're like, oh darn, I missed it. Let me look again. Okay, you have another loop, close up your container, and then side of inner lubricant. Okay, now this is very much contaminated still with this substance, so I would not want to use this for another substance. Okay, so I'm done with this one. I've made my observation, and I'm going to tape it back or rubber band it back to the container. Remember, it is still hot, so don't touch the inner. Are we good? Yes. Right. Identify as many as you can. If you don't have something at your station, is that another place you can go? You can only hold it in there for 3 seconds and then come out and go back. So you guys need more gas.
I'm sorry.
You're going to do a lot. It's going to be the single one. It should be that one. Thank you.
Other ones, I don't
They'll ask nicely from another group if they'll do a trade with you. Now there are some extras around. The extras you can add to your sheet. The extras you can add to your sheet. Who has strontium chloride as part? Hold it up for me. All right, I will hold it from here on. There's only one in the group, so one in the whole class. Alright, back with me. 3, listen, 2, be quiet. 1, eyes over here. Okay, so I have the strontium, which I know for USE, but if you have extras that are not on this sheet listed out, there's 2 extra boxes in the bottom of the left-hand data table. Like, I don't think iron is on your list, right? So you added it as another option, and I looked at one more that's on your list. VA is on your list. You can add it as another option. So, 1 second, guys. I'm talking to you. Got it? Thank you. So, after you got your full list identified as knowns, which is including this one random one that there's only one copy of, one bottle of, I have a series of unknowns. So, when you pick up one, this one, for example, is unknown number 1, so you bring it to your table, you identify it, or like the color, you bring it back. Just grab one at a time. So There are a bunch though, so you have to identify 3 unknowns correctly. So if you say, oh, unknown number 1 is copper because it's blue, then you'll understand and you're pretty confident in that one. But if there's some that you're like, I'm not quite sure with this one, then that will be the identification that I'm going to be checking. So you can list, like 15 unknowns, but 3 of them need to be correct. You understand? Okay, one at a time, thank you. We need to short. Don't leave your fingers in the plane. Release one. Alright guys, I'm going to give you about 8 more minutes in the lab. 8 more minutes in the lab. And it's orange. right, make your last identification of unknowns. Last identification of unknowns.
Yeah, reading number 4.
Alright, so we're doing prevalent plasma. Once it burns off, it starts to Alright, this is the last call for one unknown. If you last one to identify, now's the time I'm going to shut the gas off, okay? If your lab group is done and you're on analysis, cut your bunch off. Alright, gas is going on in 30 seconds. Make sure you use last one identified.
I think we need no, that's
Alright, all bus cars off now. I think we're good.
we're going to stay and there's probably no, but I need to check my notes.
Just listen up for me. 5, 4, 3, 2, 1. Listen. Look at question 6. Do you see it says choose one of your plane colors? So every group will be different here, but when you choose a color of your plane, so maybe like the one I did was blue, right? You need to determine the energy of that wavelength, right? So you don't know the wavelength just by looking at blue. But your reference tables, remember I showed you this yesterday? You can pick where blue is, you can pick a wavelength and use that wavelength to start the rapid calculation. Okay, so that is, I definitely know you need a reference table for each one six. And you guys will be close to ready. You should be very close to done. Follow the instructions on the board. Yeah, because you guys got it. You have your lab sheet.
So just these?
We're not going to be collecting more data right now. So atoms in the box.
Yeah.
And then you guys have spectrum questions. You guys can do it in your lab. Go back to your labs, like talk to each other on it. It's more collaborative. But those are the questions that you guys can get from your spectrum lab, find your spectrum lab.
All right.
That's probably enough for your lab station, so you guys have 3 sheets now.
What was the last call? Oh, yeah. I know. Oh, that's my sheet.
You guys are sharing, Ryan.
Yeah. And where's your sheet?
You guys are sharing.
So I don't need one?
Well, I think you guys
That's not what I was saying.
That's fine. I just want to make sure that's all.
That's what I was saying. That sheet, not this sheet.
Find your spectroscope lab from 2 days ago. So you guys did this lab 2 days ago, but you guys didn't use the analysis questions, so you want to do your lab questions. Bailey, you can get 2 back to your lab questions. So you guys did this lab, you guys need to find screen your target lab on your 2 days ago, and then you can analysis questions.
Thank you.
Alright guys, listen up for me. 5, 4, 3, 2, 1. Hush. Alright, raise your hand if you're done with your flame test lab and it's in the box already. Alright, about half of us. Okay, so listen up. Very soon your flame test lab should be in the box, and then you're going back to your desk to grab your spectroscope lab from 2 days ago. You have all the data, but you never got a chance to do the analysis question. So I have that here. I'm giving about 2 per lab station, so I have enough. But you will have to find your spectroscope lab. It's not going to magically appear at your desk, okay? You got to find it. Don't click the energy. Next step one. It's done? Awesome. Thank you.
Hey, you know
You
what?
just put all the mouse
I do. Do I turn this in?
So you guys look at paper. That was the place to do it. Paper. That place is out. Come on. You turn in your unit one correction.
Yeah.
Halfway done. Where's your multiple choice correction?
It should be on this thing.
Wow.
Oh, it's on that piece of paper.
What piece of paper? Where? Just turn it in?
Yeah.
So far, I have not seen you staple this, but how can you turn it out? Just FYI, I'll look at in the future, don't give me a separate. I'm going to think that for that next Corbin. Work on that now. There's never slack time here.
If we just finish number 4,
You're fine.
just skip it.